Hi everyone, welcome back. Today let's take a look at something essential to physics, and that is being able to sketch out what we call a free body diagram. Free just refers to the concept that we take what we observe, and instead of drawing out all of the detail, the fine detail of the color and exact shapes and stuff like that, we just use the basics to represent something about the shape, something about the environment. So essentially what we're doing is we're taking it out of an environment and whatever it is, the object or objects out of the environment, and we're putting something that sort of represents, not necessarily to scale exactly, but as close as possible, something about the motion. And we're going to find that motion has multiple components, not just what we visibly observe. There's other components to it, and that's physics. So let's jump in and take a look at free body diagrams. Free body diagrams. Free body just means that it is whatever object you're looking at or objects are taken out of their environment. That's really all it means. So we're using stick figures, diagrams, we're using squares, rectangles, circles, just objects, just shapes that represent whatever components we might need to define what the environment is to a minimum, so that we can then add in variables that involve our motion. Displacement variables, x or y, our velocity, any kind of force, we'll label acceleration, all the basics. All right, and then as we progress and we do other things, essentially those are always there, and then there'll be some other components that we're going to add in as well as we define out these different things. So let's just take a look at this here. So we've got a free body diagram, right? So essentially what are free body diagrams? Well, I just told you, essentially you have your object or objects that are in motion, having forces applied, some acceleration, velocity, displacement, that are taken out of their environment and represented with basic structures to represent the figures, that type of stuff. So free body diagrams, we're good to go with that. So let's scroll down here to, let's visualize an object at rest. All right, so the first thing we really need to understand is that when something is at rest, that means it's not moving. All right, at rest means that it has zero initial velocity. That's the first thing. So at rest means that the initial velocity equals 0 meters per second, and it's just not in motion. Okay, it's not in motion. It's not in motion. That's pretty simple, pretty easy to go. So let's draw a free body diagram that represents the forces acting on the object. All right, I'm just gonna erase this to get that out of the way, just so we have a clean slate here. Okay. Okay, so let's go to my little art tool here. So we've got, just need a surface. All right, just need a surface, and then free body diagram. Let's draw a square. Squares are very commonly used to represent something, unless you're working with something where it says it's rolling. Then of course you're going to use a circle. All right, something spherical. So let's go ahead and put this square object right here. Wow, this is really nice. Okay, so let's go ahead and change our color just so we can have some contrast here. So the object is at rest. So we can think of when we're at rest, it doesn't matter. This could be a tabletop for all we know, right? But this is basically ground zero. So ground equals equals 0. Ground equals 0. All right. We're at 0.0 meters. All right. What we also need to define here is this, is typically off to the right hand side. Let me go ahead and take this and move this down here a little bit. Typically in all your free body diagrams where we're looking at all of our vector quantities, we off to the right, top right corner, it's a standard, it's a convention that you write your coordinate system where you're defining, where you're showing what you're defining as being positive or negative. And so with this right here, you can see that we're defining positive in one direction and positive in the other direction as far as your x and y goes, right? So to our right, all right, we tend to think of that as being positive, and up we tend to think of as being positive as well. And so obviously this would imply that down is negative and to the left is also negative. Draw a free body diagram represents the forces acting on it. Well, gravity pulls on everything. We always go to center mass, always. And then gravity is trying to accelerate the object downward, and that gravity, we essentially get a pulling force. So it's the force due to gravity, and that's a lowercase g. All right. Since it's a downward force, since we know that force equals mass times acceleration, and that acceleration is due to the acceleration due to gravity, and we know that gravity is a negative 9.81 meters per second squared, then that means that this downward force has a negative value. All right, that is just something to keep in mind. It has a negative value. When you draw this, you typically don't put that there. You put the negative number in with your the negative symbol in with the numbers, with the values that you're using. Okay, but I'm just drawing it here so that you have some representation of that. So typically you just write force with a lowercase g, and it's understood that it's negative, and you apply that negative when you actually do the math, some plug and chug calculations. All right. So there's also an equal and opposite force. We know it's equal and opposite because this object is at rest. It has to be equal and opposite. And forces always occur in pairs. So here's our force pair right here. This is, we could say, an upward force. However, in this case, the upward force is also what is referred to as the normal force. So that's a capital F for force with a lowercase n. The normal force is always perpendicular to whatever the surface is, right? So I'm trying to get this level on the video. So right here, so you've got this surface right here, and the normal force is perpendicular to it. And that will always be the case. The normal force is always, always, always perpendicular to the surface in which the object is a part of. Okay, and so in this case, we can see here's the surface, and then obviously this right here is obviously perpendicular to it. Right? That's it. We're done with that. Let's take a look at something else. Let's take a look at another example here. We've got an object on a surface that is exhibiting a positive net force along the horizontal. So it's very similar to what we had before. So let's go ahead and get our surface again. And we've got our object. Right? And it's exhibiting a positive net force along the horizontal. So let me move this over here just a little bit because I'm already anticipating kind of where I want to put stuff. So, and that's what you should do. Whenever you work out problems, you should always think ahead of time. It's like almost drawing. Anything you do, even if you're writing a paper in English or something like that, picture where everything's going to go, and then you're just basically tracing over what you visualize. Okay? All right. So we need our coordinate system. So we're defining our positive and negative direction. All right, so exhibiting a positive force along the horizontal. So that means along the x, if it's their positive force, then it must be in motion, because remember force equals mass times acceleration. So if it has a positive force, like if I push on this coffee cup, I'm saying there's a positive force accelerating that object, and I'm defining that as my forward direction. And so now if I do this, I would call that a pulling force, and I would say that the object is moving in a negative direction. But that's still along the horizontal. So what that means is this. Since we have defined over here positive in that direction, then that means we have a force pulling in this direction, but forces occur in pairs. So there must be a force in an opposite direction in here. And you already know, you're already pretty sure of this. But if something moves across a surface, you already know about friction. So the force that is opposing this has to be a frictional force, and I'm just use a lowercase f. That has to be opposite. We know that if this is positive net force along the horizontal, so then that means in this case it's either being pushed or pulled. All right. So, but either way, whether or not you push or I'm sorry. Hang on, let me try it again. If you push, visualize it again, or pull, either way, that is an applied force. So I'm going to put APP, a lowercase APP. So that implies that it could be being pushed or being pulled, but either way, it's moving in that direction. All right, and we know that is a positive value. So now to help visualize this, now watch what I'm going to do. If it's a positive force, then that means that the amount of force being applied in this direction has to be greater than the frictional force. So since force has acceleration in it, and acceleration is a vector quantity, that means force is a vector quantity. So I'm drawing the vector with a larger value. The scale of it is larger because the magnitude has to be larger. That's why it's in motion in a positive direction. And then we still have our downward force due to gravity. And we still have our upward force, which in this case is still our normal force. Let me write that more neatly for you. You don't always write force up equals the normal force. For training purposes, I'm doing that just to help drill into your head. Right now there is an opposing force going up, and we typically say that, but this is the normal force because it is perpendicular to the horizontal. So we've got that basically draws out, that's our free body diagram that represents the forces acting on the object. So at this point, what you also need to be able to visualize is that since forces are in pairs, we're basically taking the sum of forces along both the x, and we're taking the sum of forces along the y. So on the x-axis, we have the force being applied plus the frictional force. Since that frictional force is has a negative value, right? Since it has a negative value, you can see that when you plug your number in, you would get a negative value here. So you would subtract it. If the applied force is greater, then the sum of those forces is going to be greater than 0, which is why it's moving in that direction. Okay? And then the same is here along the y-axis. We have the normal force, which in this case is the force up, and then we're going to add that to the force due to gravity. I'm putting the negative symbol in front, knowing that it's going to be a negative value there, so you can see once again if both of them are equal. In this case, we assume both the upward and the downward force are equal because it's at rest vertically. It's not moving up, it's not moving down vertically. Okay, so that takes care of this part. Let's try something else. We've got an object in motion on a surface that's exhibiting a net force as it moves down an incline. Okay. All right, so it's moving down an incline. Let's go ahead and get our picture drawn here. All right, moving down an incline. Looking pretty good. We need an incline. It looks a little more than 30 degrees. That's probably a little more like 30 degrees. And then let me go ahead and get an object on that. Wow, this is looking pretty good. All right, so now let me go ahead and get some contrast going here. We have an object at 30 degrees. We typically use the symbol theta, and then we put what the value of theta is on there for this. Okay. So it's exhibiting a net force as it moves down. So if it's moving down, it obviously has to be in motion. All right. So let's think about this. We go to center mass. So this right here is the direction is moving down, so that's the applied force. In this case, it would probably be a pulling force. We could think about it, all right? It doesn't say that something is behind it pushing it, adding to that. And then going in opposition to that, we see that there is frictional force. All right, notice I drew that vector a smaller value because it's less of a, on the scale, right? So now I'm going to use a different color here to represent this part right here, to the gravity, the downward part, the y component. That's not straight. Let me try that again. So if we're going downward, we've got the force due to gravity. That's a downward motion, all right? And again, you got your normal force. It has to be perpendicular to it. Now here we're at some angle theta. If we're at an angle theta, then it's not directly straight up. Let's think about this. So if we continue drawing our eye upward, that's where the upward force would be, all right? Your normal force is always perpendicular to where that where that surface is. If here's a normal force, and then all of a sudden here's my surface right here. If the surface is elevated, then you can see that the normal force is still perpendicular to that, but it's at the same angle in which the elevation is. It has to be. So this gets us back to our basic geometry, right? So now let me take another color here. I'm going to go with purple because I really like purple. And this right here, here's our normal force. All right? And our normal force here, it would also be at that same angle. We know that it would be at that 30-degree angle. If you take the horizontal and you pitch it 30 degrees this way, then anything else that's on it is also shifting 30 degrees in reference to where it was. That's just the way it has to be. So here we go. We have a free body diagram. Ah, that's delicious. We have a free body diagram that represents the fact that we have an applied force, push or pull. In this case, we're going to assume it's being pulled due to gravity because nothing is being added to it. Moving down that incline plane. Incline, that's why it went up. If it said decline, we would take it and we would pitch it in the opposite direction. There would still be the horizontal this way, and the theta would be basically a negative value in that case. Here we know it's a positive theta, positive 30 degrees in this case. Okay? So now that we have what essentially is a right triangle, because if you look at this right here, we have essentially a right triangle, which means we can do some trig. So let's go down and take a look at that. Okay, so if we have a right triangle, let's go ahead and get that drawn here. Got a right triangle, so we'll have the side here, and of course we've got this going on here. So you remember the whole, that whole a squared plus b squared equals c squared thing, the Pythagorean theorem, right? So we got our a, b, and c. So instead of a, b, and c, what we do is we mark x, y, and then here we put a lowercase d oftentimes. Sometimes it might be something different. We might put h. But right now, using the concept of like a displacement, we'll use a lowercase d in this case. It doesn't mean distance, it means displacement in this case. And then we have our change in x, obviously, and our change in y. So there's always an x and a y component to the displacement, to the motion. I don't care what motion we're talking about, there is an x and a y. So since we have a right triangle, we need some trig. And so we're going to, let me scroll this up, we're going to need to do a little bit of some basic trig here. So if you remember your pre-cal, there was this trick that they've taught us. It was back in the day when, way back when I went to school. But essentially, you're looking at that. So the S stands for sine. The C stands for the cosine. And the T stands for your tangent function. Okay. So sine, so SOHCAHTOA, you can easily remember that. I don't know who came up with that, but it works. There's another mnemonic I've heard of. I just can never remember it because it's the only one that I've committed to memory. So opposite over hypotenuse, so opposite of angle theta, and we don't know what angle theta is, this is just a hypothetical situation. Opposite of angle theta here is delta y, and over the hypotenuse, in this case, would be the displacement. Okay, so we've got delta y over d. Cosine would be the adjacent side, so SOHCAH, adjacent over hypotenuse, so the adjacent is the delta x over the d, over the hypotenuse, right? And then tangent would be your opposite over your adjacent. So opposite is going to be delta y over delta x. And that's it. That's it. It's pretty straightforward. We will always be resolving both the horizontal, the x, or the y, the vertical component. And then you can see here from this, basically you get a right triangle and you get an angle theta. All right. And then the Pythagorean theorem, we will use that whenever if we don't have enough data, or depending on the data we have, it could very well be that we just need to use the Pythagorean theorem to resolve a missing vector, which is perfectly fine. As long as we've got that, we're good. But when we're talking about displacement, when things move, they move in a straight line. Displacement is a straight line distance between the starting and the end point. But it is at some angle to whatever you're referencing. So that reference could be a vertical reference, and if you are over here, then you are at some angle in reference to that, or the horizontal. If you're over here, you're at some angle to that. So you need to keep that in mind. So from here on out, when we talk about displacement, there'll be a positive, negative value assigned, but then there will also have to be, we'll also have to identify the angle at which the displacement is. And so if it's above the horizontal, you're going to get a positive theta. If you're below a horizontal, let's say it's pitched downward, then you're going to get a negative theta, because obviously it's below that. And because, remember, as always, we're going to need our coordinate plane. All right. So just remember, right there, there's the hypotenuse. This will usually represent, obviously there's going to be like an initial and a final, so you can think of each of those dots as one being the initial, one being the final, depending on what's happening, depending on the direction. So it's not just x and y, up, down, left, right. There's times when we could be talking about north, south, east, and west. It doesn't matter. Just whatever is being defined. But if, say, like you're here, that's at some angle north of east is how we might say that. So just keep in mind the terms that we use are all relative to whatever the condition is that we're defining. Whatever we see in the situation, whatever we're observing with the motion, that's what we have to define when we're talking about theta, when we're talking about our x, our y, and our displacement. And there you have it. Free body diagram. You essentially need something that represents the object and a minimal amount of the environment. So in other words, again, we're taking it out. Squares, circles, lines, arrows, rays, essentially that's it. That's really all that's being done. Then of course we're assigning value to it by labeling it as velocity or force or displacement along the y or x axis. That's really it. You'll need a free body diagram. You'll need to define your coordinate system for pretty much every problem that is done in physics. If there's something where we are having to do a calculation because we're looking at all the components involved with what's happening with the motion, you can pretty much rest assured that you need some sort of free body diagram to represent it. Even if it's just something as simple as displacement, if something is motion, especially if it's at some angle theta, then we're always going to be resolving an x and a y component. So always keep that in mind. So do some physics problems, go on, drink yourself some coffee. As always, I've got plenty of problems for you to work on, and I've got answers posted for you. I'll see you soon. Stay curious. It's always good talking with you. See you at our next lesson. Bye.